We'll switch gear a little bit. Yesterday we started talking a little bit about galvanizing as a practical mean, a relatively low cost mean. So you can plan on spending an extra 20% or so per pound if you're going to galvanize the steel for the, say the steel cost you 70 cents a pound or 80 cents a pound, you can add about 20, 30 cents a pound or a little less depending on the thickness requirement that you put on. So it's a very practical solution when you consider the entire manufacturing cost. Now, one thing that I want you to think about is you can buy galvanized steel products, but a lot of times it's a lot more effective to fabricate the entire assembly and then send it for hot dip galvanizing. So typically you'll galvanize the entire product like a trailer. If you go to Home Depot and you look at their trailers, they're all galvanized. So they took together 30, 40, 50 pieces of assembly, welded it together. They need access holes so the liquid zinc can penetrate inside the tubing, and then they dip it in liquid zinc. It needs to go to a little cleaning process before that to take the rust out and everything. And when you're done, if you can galvanize it with bolts already installed, but then these bolts are need a little slightly different clearance. So it's all very practical. It's a large industry, and that's why we have these hot dip galvanizing shops. We have a few of them in the Boston area, even though we're not so industrial oriented, because any fabrication, any custom fabrication end up going through this if you're going to put it in an environment where you just don't want to have to worry about other means of protection that are more elaborate, that are more periodical. We think typically with hot dip galvanizing of a 50-year life. Now that could vary if you're in a salt area. Of course, the zinc will disappear more quickly. When we were talking about sheet galvanizing yesterday, I said that it's not as resistant. So if you do lose the paint on the surface of a car after a little while, it will start rusting. So it's not as thick, and it's already been partially oxidized to allow for the adhesion of the paint. So what I wanted to do today is give you some real practical sense of what happens during corrosion, so you don't get confused, hopefully, the way I got confused for a long time. I think that it's a very simple process. And I'll give you a lot of examples, and we'll go over different ways to prevent it or control it. Just as generality, there's a lot of different forms of corrosion. If you consider just essentially thickness reduction, stress corrosion, cracking, and pitting, so 3 of the 15 cases that you have here, you account for about 2/3 of what's happening in service. We'll mostly focus on general corrosion. I'm happy to talk to you about stress corrosion, cracking. We'll talk a little bit about pitting. But essentially, there's a lot that can happen in service with the material. We'll see galvanic here is a very small percentage, but it's very problematic. So we'll go over that as well. It's easy to prevent. A lot of these factors, if you plan ahead, you can avoid it. These are just examples of what's going on in the different processes. So uniform corrosion does lead to a surface roughness. It doesn't mean that it stays flat, and we'll go over why that happens. I think you'll appreciate a little bit more what happens after we discuss the process. On galvanic corrosion, this is an example of somebody using steel nails to put on a copper roof. It's a complete no-go because if you have the copper here, it will stay relatively shiny. Maybe it'll turn a little green, but essentially it constantly reacts with the environment, and the steel is always going to continue to be consumed by transfer of the reaction. So they have to be close enough. So if they're not sharing the moisture, you won't see the effect. But to the extent that they're sharing the moisture and they connected metal to metal, then you have a dissimilar metal issue. Crevice corrosion happens a lot with rivets on bridges. So what happens here is you have a different concentration of oxygen inside the joint than outside the joint, and that creates a battery effect by itself. It's another fairly common cause of failure. The effect of hydrogen a lot of time relates to cathodic protection. So if you impress a current on the material to prevent it from losing real thickness, sometimes you're going to start introducing crack because this protection reaction on the surface introduces a lot of hydrogen on the surface. When we were talking earlier about the pre-stressed concrete cylinder, that's what's happening there. So you build the entire system, you have these very high strength steel wires, you protect them, they won't lose any section in terms of their mechanical properties. But if you put too much protection potential, that's where you get a lot of hydrogen. And because they're very high strength, we discussed several times that when you have high strength steel and hydrogen, it tends to cause cracking. It happened with the big chain, the mooring chain. It happened with the wires. It happens with high strength bolts. So it's something to look for. There's no perfect world. Essentially, you try to be in between where you prevent the uniform corrosion, but at the same time, you don't have the hydrogen to cause other modes of failure, cracking essentially, as opposed to section loss. This is becoming a little bit more sophisticated with respect to the interaction with erosion. Perhaps one example that I'll give that is very relevant to, kind of common day life. If you own a condominium and there's a lot of plumbing in it, and for some reason the plumbers didn't estimate the flow rate correctly into a copper pipe. If there's too much flow into the pipe, you get a situation where essentially you're breaking down the protective film on the inside constantly. So there's enough drag force to prevent the adherence of a protective film, and therefore you keep corroding at a very high rate. It doesn't really happen with public water, but with well water, it can be a problem. So the circulating loops of heating water are known to have a risk, especially when you have elbows into your system, to have this type of erosion damage. And when you see it, a lot of times it's too late. So there's a lot of equations if you go to HVAC design handbook that will tell you what's acceptable. And it's not because you'll break the pipe, it's because you start losing thickness very quickly to this erosion, cavitation process. All these environmentally induced cracking a lot of times occur either because you have hydrogen or chlorides. Now, there are situations where you can't avoid having those, and then you base your material selection on that. So there's not a whole lot of process into these modes of failure, and that's why I wanted to specifically address steel today. This is an image. Oh, it doesn't look quite as good, but you could probably see the roughness here. This is probably about 4 millimeters, and it's going up and down. It's the beam structure of a tunnel in Stowe Drive. What happens there is Well, first of all, there's a lot of traffic, day and night. And they have essentially the ceiling of the tunnel's got these long beams that go from one side to the other. And there's two lanes. So there's the underground lane, and there's essentially lanes over the tunnel as well. So what they did to try to optimize the steel structure is they've put these shear transfer beams. So if there's a big truck on this location, it's also loading the beams surrounding it. So when we were talking about moment connection for building, it's done also in the tunnel. If I'm loading this beam, it's transferring definitely to the two adjacent ones. So you have a big string of these beams going this way. And what we're looking at here, this is the transverse beam, this one, connecting to the big beam. So there's a fair amount of corrosion. There's a weld, and there's some crack, some material that got removed. So why do we have this roughness? I think that by the time that we get through this together, you'll see that there's nothing too special about uniform corrosion versus galvanic corrosion, for example. So essentially, to have the removal of the metal from the surface, you always have an anode and a cathode. So if I have a little bit of a divot on the surface, it creates a site to essentially have a different concentration of iron, and that itself starts my battery from take place. So I form the anode and the cathode, and after a while, here, my concentration of iron in the solution or on the film of moisture on the surface. This doesn't have to be underwater. You've seen it in the tunnel. It's just ambient moisture. You'll get enough iron on that surface that all of a sudden the reaction stops and it transfers again. So overall, it can look relatively uniform because these anodes and cathode sites switch over from time to time. So even if I only have one metal, it will go through this anode and cathode process. That's something I don't know. Maybe you all knew this. I didn't. It always bothered me because I could only explain corrosion of dissimilar metals. I couldn't explain it as well with the same material. This one here is from that tunnel. So some of these beams had very little corrosion, and some others had quite a bit. And it's when you had an expansion joint. So there was essentially road salt coming down, and that's one of the big problems we had on the Longfellow Bridge. So one beam out of 6 had significant corrosion, and I'll pass it around because you'll see the thickness. So this came, we were working at night, and the other engineer came, hey, I think we have a problem, okay? Because we're looking at about a deposit that is 3/8 of an inch, maybe about 10 millimeters thick. Well, so it is not a very solid, it looks solid, but it's not a solid metal. The density of the deposit is about 20% the density of steel. So the amount of material lost in this case is only 1 or 2 millimeters as opposed to 10. So there wasn't any problem. The condition to have the buildup is always, as opposed to just removing it, is dependent on if you have a confined area. So this beam was essentially resting on another surface, and there was no really easy way to wash out the residue, and that's why they were building up at that location. It is a problem with bridges if you have connections. So you have the beams, and instead of having the gussets, we talked about going to the center, you have 2 plates on each side connected together. Well, when these corrode, you can essentially stretch the rivets and have the head pop out just because of that opening force. There's enough force to stretch bolts to this expansion of the corrosion product. So I don't know if it's something that is so common. I think it's good to have some understanding. So how do we prevent this from happening? Well, we were talking about the expansion joint. So yeah, if you eliminate moisture, the steel would be good forever. The galvanizing is the modern way of doing these structures. The bridge construction, the new bridge construction will typically have galvanizing, and they'll supplement it if it's near the sea with also an organic coating on top. So you all of a sudden you have two, well, it looks good as well. So you have two layers of protection, one for probably 20 years, the paint you'll be okay with, and then you have another 50-year behind you of the galvanizing. So it shouldn't be a problem that happens as much with new structures, but with old structures, when I worked on the collapse of the Minneapolis Bridge, it was 2007, 2008, that was the first thing that came out. It must be corrosion, because they did use all different kinds of salt to protect from icing conditions, and the drainage wasn't appropriate. So there was a lot going on, and I think it's been so long ago that I don't think I need to hide a whole lot about it, but there was something completely unrelated to, we said we were going to give some example of failure investigation. So there's something completely unrelated to loss of thickness that was a contributing factor. So you have the bridge that's fixed on one side, and then there's a lot of, big arch structure. So it's going this way across, and it's got a lower beam, and it's sitting on piers. So what they had on that bridge, first of all, they only had two main trusses for each side. And these piers had bearings to allow for the expansion and contraction of the entire bridge. So say this is half the span. You have 500 meters. Every a couple hundred meters where you have the pier, you have these large bearings. Well, those bearings had gears in them, and we found after the fact exactly what we see here. There's a lot of rust deposit built up into the gears, preventing them from turning. So you can start looking at where it actually broke. Say I broke about here in the main truss, and you did have a joint that had maybe 15% thickness loss, but the reason that you had a lot of loads in that area is because you were not able to expand and contract the bridge like it was intended from 50 years ago in design. So they focused on talking about the connection issue, but just the general maintenance was a problem. And I think what happens is over time it's hard for people to realize, well, I really need those bearings to work, otherwise the bridge will be in a hot condition. So one aspect that I essentially support this theory, because I don't know that it's universally agreed on, is you have enough energy. This was the hottest day of the year. So that's already work for what I'm saying. And essentially, if you prevent this one from turning, it becomes arcing and arcing and arcing. So it will introduce some load. And then eventually, you go over the deposit and overload the other way. So the idea that this was locked is the stresses here were saying, well, when it broke here, I did roll over because instead of being in a contracted condition, the bridge was in extended condition. So it's essentially a way to determine what happened first. It did start sliding out before anything started breaking at the area where everybody said this is where the first failure happened. So I think that it was conclusive with that respect, and it points to, yeah, corrosion is important, but not always in the way you anticipated it. And you can't assume that what I circulated is no big deal, that the wheel's just going to go over it, because it didn't. It had to jump over. We saw the imprint and the material even after the fact when the roller was already completely gone. Another very practical aspect of corrosion I want you to keep in mind, it is not homogeneous. So we were talking about having an anode and a cathode, but any location where you'll be having dirt around that is not all the same, it means there will be some area that are reacting more than others. They'll remain an anode for a longer period of time. So this is an example of a large underground storage tank that has holes in it all the way through. But if you weigh the tank, it's still very close to the original weight. So the fact that it gets very localized like that is always an issue when you need, to be airtight or liquid tight. So in the practice of using tanks like this, typically you could galvanize them, but it's very typical to use the cathodic protection. Now, the main disadvantage of a cathodic protection system is if the wire breaks over time, then all of a sudden you're back into your original condition. You don't have the protection anymore. So it's not really built into the product like the galvanizing. Galvanizing is very hard to lose it all of a sudden just because somebody did a digging from a certain area to another and just pull on the wires, and now you don't have any protection. Perhaps another thing that may be of interest is the idea of how fast we can expect the steel to corrode. If you are in submerged water, I'm sorry, this is in mils per year, but it gives you a very, very specific quantity. And the reason is in water, the corrosion is limited by the supply of oxygen, and there's only so fast that the oxygen is going to diffuse in the water, and therefore your rate is pretty fixed. One practical example of that, if you think of a water heater. A water heater comes with a 7-year or 12-year or 15-year warranty, and typically it's going to fail just a couple years after the warranty expired. And the reason is they know very precisely the rate of corrosion of the metal. It's not that dependent on the water. You may have some hard water that are going to consume the sacrificial anode more rapidly, but in general, it's the same for everyone. So I'm showing this chart because you may be familiar with piers by the sea where the steel will corrode more rapidly. And a lot of times it's because of the exposure to submersion and outside of up in the air again. So you essentially are washing out a lot of the corrosion product, and therefore you have a bigger corrosion rate in these conditions. In the soil, a lot of times you're going to corrode at a smaller rate than in water. It has to do with pH. It's another issue with the supply of oxygen. So in soil, it will actually very much depend on the environment. But if we think of galvanizing, we tend to use it underground a little bit the same way that we would use it above ground for drainage pipe or use galvanized a lot. So it's not super fast. There'll be applications if you're building a process facility and you know your lifespan for this process is 10, 15 years, sometimes you'll just use sacrificial thickness for your protection. So you build it thicker knowing that it will lose a certain amount each year and still fulfill the function. It was done, that was a manhole casing for a nuclear facility. They knew they had a very fixed life, they knew what they wanted to do, and at the end of the day, no galvanizing, no nothing, just the casing down in there with an extra ½ inch of thickness is what they decided. So let's talk more about how to prevent that corrosion from taking place. For steel, this is another form of an equilibrium diagram. What we have here is the pH and the stability of different oxide. What you have here is there's this special compound that allows you to, it becomes a little bit like alumina on an aluminum alloy. It is a passive layer that prevents from further corrosion. And it's a very limited range of pH, so about 10 to 12 is where you can have that passive compound that will essentially prevent the continuation of the reaction. It isolates. It's not possible for the oxygen to diffuse through that product. So that's why we do reinforced concrete. And all the pre-stressed cylinder, all those technologies are centered around the idea that as long as the concrete is in good condition, it will be in that pH range and you won't have much corrosion. It's a very effective way because you're using two materials that are not expensive, concrete and steel. I will circulate this one around because you'll see what happens when the condition of the concrete becomes suboptimal. This was only, I don't remember if it was 5 or 8 years old. It really wasn't a whole installation, but they did have a problem with cracking in the concrete. So you start having infiltration of chlorides, creates a reaction, changes the pH. It doesn't necessarily mean you need the steel to be exposed. It's really a question of how much water can get to that depth, how much oxygen, and what the pH turns out to be after those reactions are completed. So it's the most critical part of using steel reinforcement to avoid the change in the pH of the concrete. So there's more engineering to do on the concrete and its stability over time than there is on the steel itself. I say that although we have started to use a lot of galvanized rebars and coated rebars for bridges, for example, just because the engineering of the concrete is known not to be reliable. So you'll have a degradation of it, and it's acceptable as long as you don't start spalling because of the expansion of the corrosion product of the steel. So that's a little bit of a compromise, and it's been done more and more just because they haven't been able to find a really long-term solution on the concrete side. I mentioned this earlier, I'll bring it up here again, that with aluminum, we were saying we don't have a whole lot of issues with corrosion because the alumina on it is very stable, but so this is a very precise stability zone for that alumina in service. So if you have an acidic environment, the aluminum will do very, very poorly. Somebody last year in their project, they wanted to use aluminum for, kind of a special application, and they were surprised that it was corroding. So I just had them check on what exactly was the liquid they were using in that tank, and yeah, it was pH 2. So there you go. It didn't last. So it's always a trade-off. If you know you're going to be atmospheric, a lot of time it's okay, but you can have cleaning solutions. I've seen it at airports, so they'll have this very nice cladding, and then somebody has the great idea to use a pretty acidic solution to clean it, and all of a sudden it's pitted. And there's no coming back. That's always the problem with this surface reaction, is now you have to refinish the aluminum if you're going to restore it. Polished aluminum wheels for cars, the same thing. If you keep them clean, you'll make sure there's no buildup of deposit, and underneath it doesn't get very acidic. If you have a little bit of a buildup, then all of a sudden you can forget about having a polished finish. So we have the potential. So I'm looking at potential of, because you can always impress a current. So I have the dissimilar metals. That's why they make the axis more complicated. But I really want you to pay more attention to the effect of pH, because that's the most important one for aluminum. Okay. So we started with this. We said, let's use galvanizing. So the process here is just about the same, where instead of being the regular steel where you keep changing anode and cathode, you make the anode the zinc portion, and then you make the cathode your steel surface, so you prevent more reaction for taking place. So what happens on a galvanizing product is, at first, say you have no steel exposed, it's an ideal condition, then when we talk about a 50 or 60-year life, it's essentially the zinc corroding with the environment. That's what defines your life. If you have a defect in your coating, so when you put the beam on, it gets scratched, or you put the bolt, you expose some of the steel, that steel becomes a cathode automatically because of the difference in equilibrium potential. So it works as long as you always have aluminum, zinc close enough to the place where you have the damage. So if you decide that you're going to remove the zinc layer over a relatively large area, well, the center of it may not get protected unless it's really in an immersed condition. If it's just moisture, typically you can expect the droplet to travel about 5-6 millimeters, and after that, it's not protected. So essentially, it's forgiving for removing the zinc over about 5 or 6 millimeter in width. And we'll see an example of that. I was talking a little bit earlier because I've seen that a lot from mechanical, civil, structural engineers, that they'll say, okay, I will use a galvanized nail or a galvanized bracket, but you'll see here the range of amount of zinc coating that you get from different processes. So I mentioned the hot dip galvanizing because it's what gives you the largest amount of protection. You put more zinc on the surface. When they use the metallized situation, that's our thermal spray process, where you essentially arrive with the filler metal zinc and you spray it on the system. So the thickness there will vary, but you can build up to about the same thickness that you'll do with the hot dip galvanizing. You probably heard of zinc-rich paint or inorganic zinc paint. Those products essentially rely on having enough zinc particles to connect electrically with the material, and it has to be porous enough for all the electrolyte, the water, also penetrate. So it's a compromise, but it's only going to last a certain amount of time because you don't have as much reserve of zinc in this situation. So this will prevent from spallation efficiently, but it won't prevent you from corroding if you make a scratch through it. That's one practical limitation. What is typical if you buy nails or screws or some bolts even that are not specified as hot dip galvanized is a very, very small zinc layer that is put using electrodeposition. So here we're talking about 10 micrometer thickness. It's so small that the bolts work great. There's no problem with the tread. Here you're more in the range of 100 to 200 micrometers. So that's the factor of 10 that you're looking at. And it's very hard to drive a screw that's being out-dip galvanized. So you need an hexagonal head or something special about it to be able to use it. It's kind of a specialized area. Okay, so I was saying, and I don't want you to take my word for it, I said that when you put the zinc layer, you can always expect a protection if it's not submerged over a certain area. So what we're looking at here is a hole into the cladding sheet metal for a building. So you essentially erect your steel structure, then you put these galvanized steel sheets, and that's where you attach the final cladding on. So it's a sub-layer to the building envelope that's used a lot. And the self-drilling fasteners that we circulated earlier, you can use them to make this. So you don't have to pre-drill these holes, you just go right through it. So that will expose some fresh steel to the environment. And you can see on this micrograph, so our 20 micrometer here goes to absolutely zero, very next to the hole. So this view is a cut view of this region, and this distance is about the 3 or 4 millimeters, where essentially you consume the entire amount of zinc. And then because the vapor or the condensation zone is only limited to a certain area, you're not using any of the other zinc that's out there. So it's a little bit of a detrimental effect. Sometimes you're better off having a fastener that is hot dip galvanized that will have, right at the area where you expose the fresh metal, a greater source of zinc. Or you try to avoid a lot of condensation in the building. This was the New Art Museum in Denver. They have the very sophisticated titanium-looking outside, and it was meant to be a very controlled, high humidity on the inside and low humidity on the outside, and in between they needed more circulation than they actually had to prevent from extra condensation. There's not a whole lot more to know about galvanizing. You have different thicknesses. It's only going to work to the extent that the liquid is shear. That's the extent of the distance. So the most simple one, an organic coating. You can, in the case here of the old steel structure, it would be very hard to try to clean all of that, to galvanize it using thermal spray, for example. It's done. There's a lot of rework done on bridges where they'll come and they sandblast the surfaces and they put the zinc coating after the fact. But it's a slow process and it's hard to get into small details like this. So you could put a coating on, you'll see what happened. They did it once, they did it twice, and they'll do it again. So why, and that maybe you guys know, why are we having spallation of paint on steel? Because let's think of it this way. I'll give you some hints. The paint is not going to let the water penetrate. There'll be a little bit of moisture. And the most important thing is there'll be oxygen diffusing into the paint. You can't avoid it. It's organic. It has room for these small molecules. So by the time that the moisture gets to the interface, it starts getting the reaction there, is where it's going to produce some corrosion product and cause the debonding. So the life of your organic coating, so say we have our steel here, and then we have hard epoxy, because if you're serious and this is really what you want to do, I'm not talking about just painting, you know, your bike or something. I'm talking about something that needs to be a long-term solution. They'll optimize it, and with epoxy, you can have it, if it's properly set, and cured. You can have it so it will take up to, say, 15 years in immersed condition, and maybe up to 25 years when it's just moisture, for all that moisture and oxygen to get all the way to the interface to start the reaction. Now, by the time that the reaction is started, it's gone. Everything is over. You have to reapply and start all the way back from here and do it again. So I think that it makes you think a little bit about why it's never a full, a permanent solution. The physics works against you. Eventually, it will get there. It's a matter of how thick your epoxy is or any other organic coating you use. If it's just a latex paint, then it's just a year or two, or less. It's just a matter of how fast all that moisture is going to get into the surface. And you won't be able, one very particular thing here is if you do have a notch, if you have one area that's unprotected, then it starts corroding from day one. It may even corrode faster because you have a little bit of the crevice corrosion taking place. So one reason we will use it for rebars, for example, is you have redundancy. So if one rebar gets a thickness loss in one area and somehow doesn't cause the entire concrete to spall, then you're okay. I still like the galvanizing better because it doesn't build up as much product. Yes?
How thick is the epoxy layer compared to the galvanized?
You can have it, it's much thicker. So you could go up to about 1 millimeter. A lot of times you have to put it in multiple passes. And what is very critical, the same way as the galvanizing, is you need to blast the surface to create a good adhesion, because when it cures, it tends to shrink. So you're not guaranteed a good bond from day one. If you do get that initial bond, then you can build it up and be good. And a lot of times they'll have actually a bond layer that is softer just underneath the epoxy. So it's a multi-layer system. That's actually what I have here. It's an example of a fastener. They did not use the epoxy just for mounting to see what's in there, but they have a primer. No, that can't be the primer, but it's, yeah. They call it an intermediate coat. And what is not what we wanted to see here is they've put a zinc-rich layer. That was literally a mistake. They put a zinc layer. We could see, a certain distance from the steel. And it's never going to do anything good to you. And that was a commercial product. So I still can't explain why they did it. I don't think there's any reason. But it's essentially an example of a three-layer system. You'll think that it'd be a much greater cost, but when you're making things in large quantity, it's just one after the other. So instead of putting 2 or 3 layers of epoxy, you can as well put an interlayer and a primer, a bond layer, and all of that. So there's a lot of technology surrounding it, but it helped me a lot when I was looking for solutions to a specific application. The last topic about the cathodic protection I wanted to cover is if you have buried structure mostly or submerged conditions. So if you have a pump, for example, and you have a large volume of material to protect that is shared by the same environment, is where you can start dropping. So say I have the tank here, or the support structure for a large building. That's the First Church of Christ Scientists in Boston. They have they were all on wooden piles for 200 years, and it rotted, and it was one of those special type of owner that said, I want a solution for the next 150 years. Okay, so I guess we won't put wood again. And what we ended up doing is putting steel piles all the way to the rock. So you insert them, you hammer them down all the way to the rock. It's never going to move. And put a cathodic protection, so that essentially a wire connection going to these anodes into the soil. So let's say that's the bottom, that's the basement level of the church. What you do here essentially is this becomes your cathode, your anode. This becomes your cathode, and you have all the ionic transfer going through here, and you have the electrical power going the other way. The way that we had to engineer this one for 150 years is we had access to these anodes to replace them every 50 years. Because you can't go to an anode manufacturer and say, I want something for 150 years. But it was considered acceptable to the extent it was a minor operation to replace the anode after a certain period of time. Now, working in the basement of the building was an ideal situation. If you're looking at pipes, what I'm showing here is pipes where everything gets buried. So you have the anode, you have the pipe, and all the wires come together there. And you do have these access locations. You can check and see if the anode's still working. That's a very practical way of making a diagnostic of your system. But then if it's not, it's very complicated to reinsert new material at a new location. So it's really useful just to know if you, on pipes specifically, if you're having a problem. The large pipelines that transport gas or oil across the U.S. are all based on this type of technology. But it's spread significantly apart, and they will monitor the system and know, oh, got to go replace the anode or put some new one, or we didn't put enough here, or we have too much. And so everything happens, and it's because there's a variation in the soil condition. We didn't talk a whole lot about dissimilar metals, but they do happen. So I started with that, saying you have your copper nails. You have your steel nail. In reality, with the Liberty statue, it's old, right? It's 250 years old. And they are having issue with the main armature because of some copper that was used way back then, not only for the exterior, but also the nails. So if we had thought through this back then and had good electrical insulator to make those connections, there wouldn't be a problem. But when it's all built and you have essentially the water making the connection in the environment, so this is the environment correction, the electrolyte. You can have this one if you prevent the metal-to-metal contact. You're okay. You don't have the galvanic problem. And that's done a lot for connecting pipes of different kind. We just have what we call dielectric joints, and it prevents the electrical transfer from one component to the other. So it's very effective for that. So I wanted to go to stainless steel, but I think I'm just going to not have enough time. Anything about corrosion? I'll say with stainless that there are 2 or 3 ways you can have the corrosion taking place. One is if you scratch it with regular steel. So you transfer some iron on the surface, and then all of a sudden it will corrode just like a regular steel. And there are ways to figure out that happen. The second biggest issue is chlorides. So chlorides in the concentration that you have in the seawater is enough to cause this type of pitting. This one wasn't this transfer. This is just the pitting. So one way, just trying to tie back to our organic coating solution, is you can put just a little transparent. I have a sample here. This one went to hell in terms of the environment. You put a a lacquer on the surface, something that prevents the chloride from penetrating. You have moisture, fine, it doesn't do anything to the surface. So that's used a lot for architectural solutions because it's all about appearance, and if you can't prevent the chlorides completely, well, we're going to isolate this part of it. Now, what is good about it is even if the little acrylic or any kind of transparent coating you can put on is not good forever, you can stripe it off and put a new one in. So it's a practical solution because you don't need to resist the oxygen and the moisture penetration. It's just the chlorides. That's all I have today. I will circulate an email because I'd like some feedback about the different sections we did, and I think it's a good exercise for you. Say, oh yeah, from solidification I remember this, but I don't really remember that, and I'll respond to you, you know, with any questions you have or comments you have.